What we often see when we receive questions is a misconception about developing an algorithm and implementing an algorithm. Because when we cover an algorithm, we often get questions like, well, this looks a bit like another phenomenon. How and which parameters do I need to change to make it look like this phenomenon? And although sometimes it's quite possible to adapt an algorithm to simulate other phenomena by just tweaking an algorithm's parameters, most of the time what you want to do is build different models to simulate different phenomena. So how do you go about model building and implementing a model? I want to take you through this simple example of creating these dune-like or sediment-like structures. The main thing when building those models is to separate these into coming up with the model and implementing the model. And coming up with a model has nothing to do with Houdini specifically. It's just thinking about what's happening there. In the case of those wandering dunes, my thought process went a bit like this. As this is computer graphics and we are mainly interested in a certain look rather than being scientifically 100% accurate, let's just make a very simple assumption about dunes. That is, dunes in our world are formed by wind blowing sand. So this is the kind of cross-section, the side view of my dune, and this is the wind direction. And the way this dune is formed is that the wind is taking away sand from the parts of the terrain that point roughly in the same direction as the wind. So this terrain's slope in this direction is roughly pointing in the same direction as the wind. So this red area is where sand is being taken from. And then sand is deposited in the areas of the terrain that are roughly opposite to our wind direction. So this terrain's part slope is going in this direction. That's the opposite of our wind direction. So that's where sand grains will land and accumulate. And that's all there is to our model. And this is such an oversimplification of how dunes form that I literally cannot be the first person who thought of this. So if you have any papers or any links to any resources who model dunes in a similar way, or even have a more elaborate model, please let me know. I'd be very happy to see those. Just for our example, let's stick with this really oversimplified model that we just developed. And now let's think about the steps we need to take to implement this model. So this is the second part that we need to go through in order to build a model for a phenomenon that we'd like to. And this is a mixture of more general computer science, more general math, and Houdini-specific techniques. So let's go through it. The first decision that we have to do is how do we represent the dunes? In our graphics here, we see there are no overhangs, so there are no areas which, when looking from the top, form concave areas. But as we're trying to model quite a large area with dunes, our simulation possibly contains lots of details, but only along the dune's height. So this all speaks for a height field, encoding height values as grayscale values. So our area with the dunes possibly is looking a bit like this here. The next question we have to ask ourselves is how do we find the dune's orientation in relation to the wind direction? That means how do we extract the dune's direction or the direction of the dune's slope from our height field? And then how do we compare this direction to the wind's direction? As we already covered this in a few other videos, let me just mention here that we're going to use the gradient. And the gradient of our height field, for example, at this point, which could be this point in our dune's cross-section, is resulting in a vector pointing in the direction of the steepest ascent. That means the gradient of our height field on this point might point in this direction, and that tells us that the dune's main direction is exactly the same as this vector of our gradient. And this is not really Houdini specific. This is just basic math or advanced math, using the gradient to extract a directional vector from a two-dimensional function. And finally, how do we compare this direction to the wind's direction? The blue vector here being the wind direction, the red vector being the direction of our dune, the gradient of our height field. And what we want, rather than an angle, is a value that tells us if we need to deposit or if we need to take away sand from our dune. That means from our height field. And for that, we're going to use the dot product of normalized vectors. So in here, V1 is my normalized gradient. That means it has a length of 1. And V2 is our wind direction, again normalized to be a length of 1. And the orange number here is the angle between those two vectors, called alpha. And the dot product of those two vectors, which can be two-dimensional or three-dimensional vectors, ranges from 1 to -1. The dot product is equal to 1 if these vectors point exactly in the same direction, so the angle between them is 0. The dot product is -1 if they point exactly in the opposite direction, so the angle between them is 180 degrees. And the dot product is 0 if the angle between them is 90 degrees, so if they're perpendicular. What that means is that if these vectors point in the same direction, so if the direction of the dune is exactly the same as the wind direction, then we can subtract this value here from our dune's height, thus simulating sand being taken away from the dune. And if the direction is exactly opposite, we can subtract -1 from the dune's height. That results in +1, so sand being added to the dune in these areas. And any values in between will account for the wind not hitting the dune perfectly at the same or opposing angle, but angles in between. So this is the second element that we need to think about when developing algorithms to simulate phenomena. In here, we took our general idea and broke it down to several steps that we can perform one after another, and thus have a mathematical recipe of how to simulate our dunes in this case. And this is called an algorithm, kind of a recipe, a mathematical recipe, a set number of steps that we have to perform in order to arrive at a certain result. The final element in this process is implementing the actual algorithm, and that's what we love doing in Houdini. So let's get started here. I'm gonna drop down a geo first, dive in there, and as mentioned, we decided on doing this on a height field, which in Houdini is a volume. Let's drag this down, call this scalar volume height. Let's check two-dimensional, make this a ZX plane, and increase its size to say 10 by 10 units. Also in our properties tab, let's make sure the display mode is set to height field, so now we can see the resulting height field we generate, which is perfectly flat for now. Next, let's model an initial landscape. In our case, just using a noise, this time using a volume VOP, as this is a rather easy way getting intricate noises using the unified noise. In our case, we can use the static noise because we only need it once to initialize our height field at the beginning. This takes in the position, and then let's bind this using a bind export to our height parameter. Like so. Let's make sure this outputs a 1D noise, one-dimensional noise. That's right. Let's link this up, and we can immediately see we are getting some sort of weird height field here. Also, as we're seeing these jagged edges, let's go up one level and increase the volume's resolution. Drag this down, go to dimensions, and let's increase this to say 2K along each axis. So 2048, like this. And now we have a more detailed noise in here. Let's dial in the noise a bit, enabling a terrain fractal to give this a bit more detail, dialing back its frequency, decreasing its amplitude, and that looks like a decent initial height field. Let's go up. Next, let's create some controls for the wind direction. So while we could just initialize the wind direction with a single vector, making the wind point perfectly in one direction, what I'd like to do is use a control spline, so we'll be able to kind of draw in our wind directions. For that, I'll just press space and 2 to go to the top view, and then I'm gonna drop down a curve node, go to its tool handle, and just draw a somewhat coarse, jagged curve like this. Let's have a look at this in three-dimensional space. That's fine. And this curve is a bit coarse, so let's resample it, making sure we resample it as a subdivision curve. Let's highlight this and see how many points we have in there. Well, let's say a decent amount. Let's maybe increase it a tiny bit, like so, and make sure we calculate its tangents, which are going to be the vectors that we'll look up, and this is going to be our wind direction. Let's just briefly visualize them. Here they are, maybe a bit dense. Just let me increase the sample length. So you can see we've got vectors pointing roughly in this direction. Let's drop down two nulls, call one in_grid. This is going to be our height field, and call this one in control curve. Now, the whole algorithm we talked about is going to be executed over and over again. So let's use a solver, drop that down, wire in the grid in the first and the control splines in the second slot, and dive in there. First thing I want to do, just to be clean in here, I want to drop down a switch, wiring the previous and the input 1, and making sure that we switch to input 1 only on the first frame, because on the first frame there is no previous frame, using a quick expression $ff equals to 1. So yeah, that worked. And now let's use a volume wrangle to program our algorithm. Takes in our volume and our control spline. That's the spline coming in through our second slot. The first thing I want to do is I want to have a slider to be able to control how much sand is taken away or deposited in our simulation steps. So let's call this one amp. And let's use a float slider to dial that in. Let's create the slider. Here it is. Let's set it to maybe 0.02 for now. We can dial that in later. Next, I want to find the nearest point on my control spline. So let's do that using the near point function. NPT, that's short for near point, equals to near point. And we want to find the nearest point on the control spline. That's the spline coming into the second input slot on this wrangle, meaning ID of 1. And we want to find it in relation to our currently active voxel position, like that. Next, from this near point that we just found, we want to look up the tangent u vector. That is the direction of our wind. So let's do that. Vector dir, let's call it dir for direction, equals to the tangent u value on our nearest point, coming in through the second input. Next, we need our height field's gradient. So let's calculate that and call the gradient vector grad, using the volume gradient function, and we're going to point that to our current geostream, and to our first and only volume with the ID 0. Let me just check. We also need a position here, so it's going to be V at P. Next, let's calculate the angle between our wind direction and the quote-unquote direction of our dunes, and call the resulting value angle, although it's not technically an angle in degrees. And like we mentioned, we're going to use the dot product between those two normalized vectors, dir and grad. Again, when the vectors are pointing in the same direction, this value should be 1, and if they're pointing in opposite direction, this value should be -1. And we said when the vectors are pointing in the same direction, we want to subtract this value from our height. So let's do that by just subtracting our angle from our height. But before that, let's multiply it with our amplitude so we can dial in the strength of the effect. Like so. That is looking strong. Let's just append a null here. Call this one out. Highlight it. Let's go up one level, save this, highlight our solver, and let's let this run for a few iterations. And that is really strong and really jaggy, high frequent. So what we might have to accommodate for is that sand usually does not pile up in a single spot, but gets distributed around a certain area by the wind. And we can simulate this by, in here, using a volume blur to smooth out those deposited values a bit. So let's drop down a volume blur in here, set this to use the voxel radius, just one voxel for now and one iteration, drop that down in here again, go up one level and hit play again. Still a bit strong, so let's increase our volume blur value to maybe a radius of 2 voxels. That's looking a bit more promising, but I just have a feeling that our amp is too strong, so let's maybe add another 0 in here, making this effect only 10% as strong as previously. Again, resimulate. And yes, after quite a few iterations, we're getting somewhere. I think now I can dial back the strength of the blur to smooth out these dunes a bit less. And maybe what I also want to do is compare my current voxel value to the spline position, so that the further we get away from this control spline, the less my height field is affected by the vectors of this control spline. Let's reset this, save this, go into the solver, and in here I want to decrease my voxel radius back to 1. And also, in here, where I do all this sand transport, I'd like to introduce a distance measure to measure the distance from each height field's voxel to the nearest point on the control spline. Let's do this up here. After we looked up the point's tangent, let's look up another vector, the nearest point's position. So let's call this one npos for near position. And that's just the nearest point's position value, like so. And now let's calculate the distance. Call this one d. And it's the distance between our current position, current voxel position, and the nearest point's position. And also maybe after that, let's just remap it so it does not range from 0 when it's really close to whatever value, but it ranges from 1 when it's really close to a fall off value, say 0 when it's 3 units away. So let's use a fit function, and we want to fit d, our distance, which before remapping should range between 0 at the closest and maybe 3 at the farthest point. And after remapping, it should go from 1 at the closest point to 0 at the farthest point. And now finally, we have to multiply in this distance factor down here. So we now have a distance fall-off modeled. And using these remap parameters, we can dial in how far out we like the control spline to affect our height field. Okay, save this, go up one level and resimulate. And now we can see we have this sedimental wind blowing effect only in these areas that are close to the control spline, making this whole thing look more like a riverbed. And in this case, our sediment being blown around not by the wind, but by water. So a really simple model that we developed here. And the point of this tutorial should not be how to simulate the perfect dunes or perfect sediment. I rather want to give you an idea about the steps involved when building a simulation to model a certain behavior that we observe in real life. And it's those 3 steps again. And let me just repeat them. So the first step is developing a general idea. That means breaking down our real-world problem into a simple set of steps that we can then turn into an algorithm. That means mathematically describing those steps, which we then finally implement in whatever environment we want or need to use. In this case, Houdini. With the 4th step that we kind of overlooked here, being tweaking our parameters. When diving in here and tweaking our amp and our volume blur values, that's actually the fourth step in your modeling process, which is what, as a TD, you'd prefer leaving to your artists, to be honest. So next time when you're seeing a natural phenomenon and asking yourself, would it be possible to model this phenomenon using algorithm X, Y, or Z? Think about if the algorithm really fits the problem, and if the problem can be broken down into those certain steps that a certain algorithm has, or if you need to rather develop another model. And make sure you get the distinction between a model and its actual implementation. Alright, that's it for this bit more conceptual episode. If you want to support us, like what we're doing, want to get access to more in-depth courses, consider supporting us on Patreon. And for everyone doing so, thanks so much, with a very special thank you going out to Parasol Island, Gearbox Studio Quebec, Encore VFX, Important Looking Pirates, Chris Hebert, and Rafik Anadol. Thanks so much, guys. And until next time, it's cheers and goodbye.